Hi everyone, I'm Raghavan. I'm from Pleasanton, California, and I'm currently a junior in high school. Ever since gravitational waves were discovered, it has been clear that they have the potential to revolutionize astrophysics, from black holes to the nature of gravity itself. Today, I will be talking about how to estimate the mass and distance of black hole mergers from just the gravitational wave received, as well as the importance of the fixed values the other parameters are set to. In 1915, Albert Einstein theorized that if massive objects accelerate, they would shake the fabric of spacetime, sending ripples across the universe carrying information about their origins. In 2015, these gravitational waves were finally detected from a black hole merger, proving Einstein's work to be true. However, only extremely violent cosmic events, like black holes merging, can cause waves strong enough to detect and measure from Earth. There are four types of events that can cause a gravitational wave, out of which only one has actually been detected by the LIGO detector. This event is the in-spiral, which I will be focusing on today. In-spiral gravitational waves are caused by the end of a binary system, when two objects merge and become one. As the two objects get closer and closer together, they speed up until they collide. This causes the frequency of the gravitational waves to get higher and higher until it forms a chirp at the moment of collision. Stochastic waves are gravitational waves from the earliest stages of the universe, much earlier than the cosmic microwave background. Continuous waves are caused by systems that have a constant and stable frequency, like black holes orbiting each other or stars rotating on their axis. Burst gravitational waves are little blips that are caused by really short, unexpected events. Not a lot is known about these ones. LIGO, the Laser Interferometer Gravitational Wave Observatory, is the primary observatory used to detect and measure gravitational waves. It has two interferometers, one in Louisiana and one in Washington. The advanced LIGO detectors have two perpendicular arms which each end with optical mirrors. When a gravitational wave reaches the detector, one of the arms is stretched while the other is shortened a tiny amount. The difference shows when a laser is sent through each arm by way of a beam splitter. It hits the mirror at the end and returns, but when it hits the beam splitter once more, the lasers are recombined. In this process, the wavelengths have been shifted slightly in order to achieve total destructive interference when they come back together. However, since the length of the arms have been changed by the wave, the recombined wavelengths don't match up properly thanks to the gravitational wave. This is a simplified explanation, of course, since the LIGO data is actually very noisy. LIGO uses these measurements to construct simulations of gravitational waves and black hole mergers and use them to understand each other. We can use the gravitational waves detected in order to find out more about their sources. In this case, I'm using 3 gravitational wave signals in order to find out the masses and luminosity distances of the mergers that cause them. The entire method was based on Bayesian statistics. The main goal is to estimate the posterior distribution, which is the parameters being a certain value given the data observed. This observed data is actually the likelihood of the data given the real values of the parameters. We use this likelihood in our prior knowledge of the parameters in order to estimate the posterior distribution. Markov chain Monte Carlo is used to estimate the parameters of black holes, Monte Carlo being a technique that randomly generates samples, and Markov chain meaning that each step of the system is based on the current step. MCMC methods create walkers which move around randomly looking for places with a higher probability than the current area. In order to prevent the walker from getting stuck in an area with a local maximum instead of the overall one, we use a variation similar to one called Metropolis Hastings, which is a basic algorithm that's more accessible to explain. When a new step is proposed, the ratio of the new step's probability to the current step's probability is calculated. This ratio is compared to a randomly generated number between 0 and 1 and will only move to the new location if the ratio is greater than that number. This means that the walker will always move to an area of higher probability, but sometimes to an area of lower probability, allowing it to keep moving even if caught in a local maximum. The code itself relies on the programs Bilby and Dynasty. Bilby is a library that can access interferometer and gravitational wave data and use it to generate waveforms and calculate likelihoods. In order to actually perform nested sampling, Bilby uses a sampler called Dynasty. Dynasty actually does the MCMC process, while Bilby is more a general framework for estimating the parameters. While estimating all of the parameters together would provide the most accurate results, it would also take days to process. Instead, I needed to assign pre-existing values to all of the parameters except for the 3 I want to estimate. Those 3 are the chirp mass, which uses the two masses to determine how quickly the frequency increases as the black holes approach each other. The mass ratio, which is the ratio between the two masses, found by dividing the smaller mass by the larger, and the luminosity distance, which uses the relationship between the brightness of the object from Earth, the apparent magnitude, and the brightness of the object 10 parsecs away from Earth, the absolute magnitude, to measure how far away the object actually is. We're also going to be looking at the phase, which is where the wave is in its pattern of oscillation, which ranges from 0 to 2 pi. While I'm using the actual values measured for the set parameters, I will be experimenting with a phase parameter, I'll be running each event 3 different times, each with a different value for phase in order to see how it affects the mass and distance. There are several other parameters, but those will stay fixed. In this project, I will be using 3 different events. GW150914 was the first gravitational wave ever detected, and the first black hole merger ever observed. Each gravitational wave event is named after the day, month, and year of their detection. This frequency time graph, over on the left, shows the intensity the signal received. The x-axis is the time over which the event took place, while the y-axis is the frequency that LIGO detected. The normalized energy is the strength or amplitude of the signal at that moment. The more yellow it is, the stronger the signal. In the case of GW150914, the graphs follow the black holes getting closer and closer before they merge, producing a much stronger signal. This sharp increase in strength and frequency is called the chirp. The strain frequency graph on the right shows how the detector is able to detect gravitational waves at different frequencies. The x-axis shows the range of frequencies the detector is sensitive to, while the y-axis shows the strain sensitivity, which is the smallest strain that the detector can measure. The lower the y value is, the more sensitive the detector is at that frequency. The spikes are where the instrument picked up noise. For example, around the 60 Hz point, there was a spike caused by the imperfections in the electromagnetic shielding. The large spike at 900 Hz is caused by the fiber suspending the beam splitter. GW190521 was caused by the largest black hole merger to date. From the frequency time graph, we can see that the signal was pretty strong due to the sizes of the black holes involved, but the details aren't as clear because it was so far away. The range of the amplitude spectral density is also larger because it starts at almost 10 to the 21st, unlike the others. There are spikes like the previous graph, mostly due to the materials of the detector itself. The event GW170814 was the first event to be detected by both detectors of LIGO as well as Virgo, another gravitational wave detected. The frequency time graph clearly shows the stages of the merger as they circle closer and closer before they release most energy when they merge. The strain frequency graph is also much more stable than the others, except for the 900 Hz spike caused by the fibers holding the beam splitter. After running each event 3 times, using a different phase for each time, I got 3 different corner plots and 3 different estimates for the masses of each black hole. In the corner plots, we can see where the walkers from the MC-MC sampling finally converged, the area with the highest probability for the chirp mass, mass ratio, and luminosity distances. Then I can use the chirp mass and mass ratio to find the masses of the 2 black holes. However, we know that there will be a lot of error due to the fact that I only estimated 3 parameters instead of the full 15. Since I tied those parameters down to a single number, the relationship between the parameters caused the values of the chirp mass, mass ratio, and luminosity distance to be skewed. This is exemplified by the use of the phase parameter. By only changing the phase parameter, we can see the sizable effect it has on the outcome. In the case of GW150914, the mass is already different from the true value, but just changing the phase from 0 to 2 pi over 3 caused the chirp mass, and therefore the black hole masses, to jump up significantly. However, bringing the phase to 4 pi over 3 caused the masses to return to a similar area than where it was when the phase was 0. The luminosity distances followed a similar pattern, though at a smaller scale. The mass ratio, however, does the opposite, since it goes down when the phase is 2.094. The same thing happened for GW190521. The standard deviation for the luminosity distance is very large, causing many of the value and parameters to stray away from the real values. Despite this, we can still see the wave significantly jumps up when the phase is 2.094 and returns when the phase is 4.189. This is especially noticeable in the luminosity distance, which changes by 2 to 300. GW170814 reveals something different. The variations between the chirp masses, mass ratios, and luminosity distances are much more subtle and don't seem to follow the same pattern as the previous 2. When I originally ran the code for these 3 events, there was one key difference between this event and the last 2. When assigning values to the priors, the first 2 events had more available values for the priors than this one. Since I had less real values, I had to set much more of the parameters to 0. However, this meant changing the phase value was less out of place, causing it to overall affect the masses and distances less. When we put the results of these 3 events together, we can see the patterns more clearly. GW's 150914 and 190521 followed a similar trend, while GW 170814 only had some subtle shifts. Gravitational waves are incredibly important to the future of astrophysics, and using Bayesian statistics and Markov chain Monte Carlo methods, we were able to analyze gravitational wave data from 3 different black hole mergers to estimate their masses and distances. We can see a clear pattern where changing the phase causes significant shifts in the estimates, highlighting the intricate relationships between all the parameters involved in determining the masses and distances of the black hole merger. Better understanding how different parameters influence the estimation process can lead to so much more accurate results in the future, greatly enhancing the precision of gravitational wave measurements, which, in turn, would better our knowledge of the sources of these waves. Thank you so much for listening.